Alrighty, so we didn't really touch on boundary layer stuff, and it's very important. So let's get into that. And then what we're going to do is we're going to look at our inflation layer on the car model, and you're going to tell me whether or not you think it's a good inflation layer. So to reiterate, K omega turbulence model, that's the main one we're usually going to be using. I used SBES in the other case because we're looking for sound analysis. So that's something very specific where we need to pick up that turbulent behavior directly. Most of the time K omega, which is a 2-equation model, we have our K, which we've spoken about to be our turbulent kinetic energy, and our omega. And what these are our Navier-Stokes equations, just reappropriated with K and with omega. So our time dependent, our convection, our diffusion, and our source terms are all in there. And each one for our K and a different one for omega. So remember that K omega is the most useful one for most cases, and it has what's called our shear stress transport model. And what that does is it tries to pick up what's happening in the boundary layer very accurately. Okay, so the boundary layer is a very complex flow field, and it's very small in most cases. So if we were to model it directly, we would need ridiculously small mesh elements to do a DNS of a boundary layer. So we use K omega. So our turbulent boundary layer consists of 3 distinct regions. We've got our viscous sublayer. So in here, we've got our turbulent or buffer layer. So that's in this middle one. And then we've got our outer layer or our log law layer. Okay, so you can see here that as we move away from the wall, so at the wall, the velocity is going to be 0. And as we move away, it's going to be increasing towards some free stream. But that profile there is very specific and it's very important. Okay, so as you get further away from the wall, the velocity is actually increasing at a much slower rate. At the wall, it increases quite rapidly with respect to the changing distance from the wall, and then it kind of levels out to become kind of a log law thing. So linear at the start, transition, log law. All right, so those are really important. So that's the velocity versus distance. If we plot it on the log scale, which is the next slide, that's a little bit misleading. But the next slide is log law. You can see here that we've got, with increasing distance from the wall, the velocity is increasing, and then it becomes linear on a log scale. Okay, so we've got our viscous sublayer. We're actually increasing with the in a linear fashion from the wall. It's actually considered to be linear, but on a log scale, it looks like exponential. And then there's a buffer layer, and then our log law, which on a log scale looks like a linear. Okay, and that's a common shape for all boundary layers, basically. The size changes, so this is U plus and Y plus, and those values are important. So they're non-dimensional values. So this is constant. The actual velocities change based on, you know, the length of the boundary layer, the velocity of the free stream, all that kind of stuff, the viscosity of the flow. But this basic shape remains constant. In the near wall region, the gradients are high, and accurate calculations in the near wall region are paramount to the success of the simulation. Okay, so there's 2 ways to do it. We're using wall functions or resolving the viscous sublayer. Both of these are using modeling. We're not actually directly modeling, simulating anything. We're still modeling, but there's 2 different methods in using the K omega SST model. So using wall functions, basically we are looking at from about Y plus equals 30. I think we need to go through what Y plus is first, if we have it. Let's go back to this slide so I can explain properly what Y plus is. So these values, like I mentioned before, are non-dimensional. So U plus is a non-dimensional value of velocity. So that'll be non-dimensionalized with respect to what the actual free stream velocity is. Y plus is our distance from the wall, and that just tells us where in the boundary layer we are. Because as we said, the actual size of the boundary layer is going to be different for different flow regimes, but this shape will be the same, and the Y plus tells us where we are in that boundary layer. Okay, so on here we've got our Y plus, so between 0 and about a Y plus of 5, we've got a viscous sublayer. Between 5 and about 30, we've got the buffer region, and then from 30 up to 500 plus, we're in the log law region. Okay, so those 3 distinct regions are represented by a Y plus value. So when we're using wall functions, K omega SST, like I said, has 2 different methods. We're looking at either using wall functions or resolving the viscous sublayer. Using wall functions, the first cell should be in the log layer. Okay, so it's a much bigger first cell height, much taller first cell height. That's going to reduce the mesh count significantly. Okay, typically have a Y1, which is our first layer height of between 30 and 300. We want to aim for 30. Okay, because that's the method, that's the value within which the turbulence model has been validated for. When we're resolving the viscous sublayer, we're looking at a Y1 that needs to be equal to or less than 1, our Y plus. Our Y1 needs to have a value of Y plus of 1 or lower. In both cases, we need enough boundary layer elements to pick up the gradients. So we need a lot of boundary layer elements, similar to what's on the left. So on the left, we've got our resolving the viscous sublayer. We're looking at our Y1 with a Y plus of 1 and enough elements to capture the gradients. So this is our wall. Our flow will be going in some direction, you pointing to the right. So our flow is going to the right. We've got our wall, we've got our boundary layer. And these are our mesh elements that aim to pick up that boundary layer. So when we're resolving the viscous sublayer, we're using a lot more mesh elements than when we're using the wall functions. This is a little bit misleading, because when we're using the wall functions, we still want to have at least 10 boundary layer elements for a, which are called inflation layers usually. We still want to have about 10 inflation layer elements to pick up the gradients in the boundary layer outside of the Y plus of 30 region. So I've got a very dry throat today. So the 2 different methods. In either case, we need to have a lot of elements. Now, actually figuring out what our Y plus is, you can have a good first guess using certain calculators. You can look it up. There is a formula for it. We also have a calculator that we've created for it. So a target, you'd put in your target Y plus, we'll put in our velocity, we'll put in the length and our density and our viscosity. And what can we tell about that? We can tell that we're looking at something that's very Reynolds number specific. Remember, Reynolds number is velocity times length times density over the viscosity of the fluid. Okay, so based on our Reynolds number, we know what the height of the Y plus is, generally speaking. Obviously, it changes, but we can get a good first guess. Now here's Hashan's created some examples, some test cases to go through what it looks like when we're resolving the boundary layer properly. So when we're resolving the boundary layer using resolving the viscous sublayer, we're looking at a Y plus of 1 and a bunch of layers coming out. Obviously a Y plus of 30, we're going to be using much less elements, far fewer elements. So that's important if we're doing FSAE. We don't always have the computational resource to resolve a full car for Y plus of 1, but we know using K omega SST that it has a model built into it to resolve to make an analytical assumption about the boundary layer if we start from boundary layer Y plus of 30. Okay, so we know that we're maybe at the cost of accuracy, but there's a model built in to do this. So this is the kinds of things we're thinking about when we're resolving the boundary layer. So you can see here what we've got plotted, I assume is velocity, because it's the smallest at the wall and then increasing outwards. And you can see that the velocity vectors are increasing away from the wall. Okay, and this is obviously, in this case, we've got a lot more elements right down the bottom. In this case, we're going from a y plus of 30. But in both cases, we need to have enough inflation elements to pick up the full boundary layer. So you can see in this case, the boundary layer goes up to about here, and we've got elements that cover that quite comfortably. Same with this one, our inflation layer goes all the way up to here. So that's really important. And that's just basically the way the models have been built. These two equation models, the K epsilon and K omega, they're both the same in this regard. They're validated for boundary layer resolutions that are aligned with the flow. Okay, it's a more efficient method and a more accurate method of understanding what's going on in the boundary layer. That's why we have inflation layers. Okay, you can see here that if we have different levels of boundary layer resolution, we're going to get different understandings of what's going on in the flow. And this is a pressure, basically a plot of pressure on the main wing of the wing that we were looking at. You can see here that the difference between a y plus of 1 and a y plus of 100 is quite large. The difference between a y plus of 1 and y plus of 30 is not that great. Okay, we're assuming here that y plus of 1 is the most accurate, and the relative error between 30, 60, and 100 is different based on, you know, how well that boundary layer is being resolved. So another one just goes through very quickly the amount of layers in the boundary layer. You can see here, when we're resolving to a y plus of 1 in all of these cases, we're not really actually picking up the full boundary layer until about 30 layers. Okay, so it's really important that we have quite extensive boundary layers, inflation layers, to pick up a boundary layer properly. Okay, so even 25, you might give that a pass, considering computational expense. If you don't have the kind of resources that some people do, you may be able to cut it down a little bit, but you really need to be for a research level CFD solution. You want to be having inflation layers that cover the boundary layer quite well. Okay, so let's have a look at our model. We can see it's finished solving. And we're going to have a look at the just the mesh on the symmetry. We're going to look at all the faces, all the edges. I'm going to put on manual because the color's better. So that's our inflation layer. It's pretty pathetic, really, isn't it? Obviously, this is just a test case, but when we're running our own analyses, if we were to actually do a car model, we need to have a good understanding of what our first layer height is and how many elements we need to resolve that boundary layer. So if I was to plot vectors on the symmetry plane, and then let's have a look at put this wall back on. Add this one to graphics. So we can see here that the actual reduction in velocity, like as a function of the free stream, is not very large at all. So we're not even, the boundary layer is all in here, really, between these two cells, and we're not picking that up at all. So it's really important that we understand that when we're doing that, we're not doing it with best practices, and we're probably getting an incorrect result. I think it's important here to say that the reason that it's really important to pick up the boundary layer, it may seem, you know, arbitrary. It's not, and the reason is because of how much is happening in the boundary layer. So basically, what we have is we have this viscous sublayer that's all laminar flow, and then it turns transient, and it becomes transient in that buffer layer, and then goes into the log law layer. Where that boundary layer actually turns transient has a huge effect on aerodynamic properties. Okay, so it's hard to make general comments about it, but there's things to understand, like a turbulent boundary layer will stay attached for longer but will create extra drag. Okay, and that's all of that happening in the boundary layer can have huge implications for what these results are. So if we're not picking up the boundary layer accurately, we're changing where the flow is separating, how much friction drag there is between the from the airflow on that surface, and we're changing our result. So there's a lot happening in the boundary layer, and picking it up accurately is very important, especially for things like external aerodynamics. Cool. So in this case, yeah, we definitely need a much better inflation mesh to pick up what's going on properly. One thing I will show as well that we can do in here is we can actually look at our Y plus value. And now I'm expecting probably a minimum Y plus of about 100 here. And it'll come up on the legend, but let's plot the Y plus value on all the walls except the ground. And we're looking at a minimum value. We're actually getting a minimum value of around 0.5. So in some cases, because of, say, maybe separation and the size of the boundary layer has grown significantly, we're actually getting Y plus values within the viscous sublayer. But there's a lot of regions where we're going a max of 500. Actually, if I take off global range, we'll get a better understanding of that. So we're getting a maximum of 256. So in these regions here, we're really not picking up the boundary layer good enough. And this region here is really critical. So when we're doing an FSAE cut, one of the hardest things to analyze properly, and also one of the worst performing components on an FSAE cut, is the wheels. So we can't cover them, we're not allowed, but they create the most drag, and they also generally create lift rather than downforce. So picking up what's going on with the wheels is very important. So if we've got a boundary layer of, you know, a Y1 height of 257 on this wheel, we're not really going to be sure that we're picking up the right behavior, as in we're not going to be resolving the pressure gradients in the boundary layer accurately, which means we're not going to be picking up where the flow's separating accurately. And where the flow's separating and how turbulent the boundary layer is, as I mentioned before, are critical to understanding aerodynamic performance values like drag and lift. One thing I want to touch on very quickly is the GEKO model. Okay, so the GEKO model is another turbulence model. If any of you guys are really interested in CFD and want to do CFD for your final year project, I would encourage you to do something on the GEKO model. It's very newly released. Okay, and what it is the generalized K omega turbulence model. So it's basically K omega, but it has coefficients. Okay, these coefficients we can actually play with when we look at the jump out really quickly, K omega model by itself. We've got all these coefficients. Never touch them. Okay, never ever touch these, because playing with these can really just stuff up the model, and it's no longer validated for any scenarios. Okay, whereas if we look at our K omega model, these you can change these values, and it'll change certain properties of the model without really stuffing up fundamentally what the model does. Okay, so if you are interested in that kind of thing, that's why I say it would be good to do a research project on it, because you can really play with these coefficients. There's a separation coefficient, a mixing coefficient, near wall, jet, corner curve, and they change the characteristics of the flow in subtle ways that allow you to tune the turbulence model for your specific application. So basically, if you were representing what was going on in a wind tunnel or some other place where you could be monitoring the flow and you're trying to represent that in CFD, you can tune the model to represent that more closely, and then you know you've got a model that can be used for other scenarios that you don't have to keep tuning for. Okay, so if there's a specific application, like you're running a car in a wind tunnel and you tune your GEKO model, so you would in this case tune CSEP, which is your separation coefficient, to have the same separation bubble as what you would see in a wind tunnel model, then you can run different CFD models with a greater confidence that your model is correct for your specific application. Okay, so when you want to change the wing and you want to put the wing in different configurations, you can do a lot more in CFD because you've tuned your turbulence model to suit. So you can see what we're looking at here. We're looking at the trailing edge of the wing where the flow separates. So when the flow is aligned with the wall, it's going to be coming up from the wall directly right. So we've got our GEKO 2.5, so that's our CSEP is equal to 2.5, CSEP 2, CSEP 1.75 down to 1. So you can see here that our purple one goes left at the start because we've got our highest CSEP coefficient. It's going to separate the earliest. And so that purple one separated in here. We've got our purple one separated, our red one separated, our green one, and our orange one. If we don't call it separated now, it's at least definitely separated post that point. Whereas with a GEKO, with a separation coefficient of 1, it's still attached at the trailing edge here. Okay, so these are very subtle differences. And like I said before, when we play with the coefficients of a K omega model, we can destroy the model. When we play with the coefficients here, we can kind of change the separation behavior without affecting the other behavior too much. I don't know how they've done that. It's like magic, but this is a new model and something worth looking into if anybody's interested in CFD. So in this case, we've got our near wall, and we're looking at the changes in behavior of a backward facing step, the changes in the separation, so where it separates. So we've got our coefficient of friction on this wall here. So our coefficient of friction is going to be positive with the flow direction when it's reattached. So you can see it starts at 0, it's negative, 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 and at this point, or when it reaches 0 again, it's reattached. Okay, so obviously you can see that the changes in the reattachment point is a function of the C near wall. Okay, our near wall coefficient. Okay, that'll be in the slides if you want to go into that in greater detail, have a look at that. Alrighty, let's have a look at some heat transfer modeling. Okay, so you can see here our energy equation. So we're adding in an extra equation when we tick that button, and that is basically just modeling the transfer of energy through the flow field. And energy is temperature, basically, generally speaking, in most cases. Okay, so we need to turn that on whenever we want to consider temperature in our flow domain. Now we look at our energy equation when it's applied to our Navier-Stokes. We've got our unsteady, our transient component. We've got our convection component. We've got our conduction, diffusion, and dissipation, all under the one diffusion bracket. And then our source term. Now, when we want to understand heat transfer, we've all been through this in our engineering. We've got conduction, convection, and radiation. So if we want to do a heat transfer problem in CFD, we need to make sure that we're modeling conduction, convection, and radiation where appropriate accurately. So conduction is the first one, and we are looking at our Q value. We can put that in our thermal conductivity for our material. Okay, so generally it's going to be our solid material, and that'll come up when we turn on energy equation. The next method of heat transfer is a convection. Okay, and CFD is the best way to pick up convection, right? Because generally what you do in FEA or other analytical methods of understanding heat transfer, you have some coefficient that you've assumed based on either testing or some assumptions that you've made, and that H value is really important. So the H value is how much heat's being transferred for a different base for this temperature difference, the temperature of the body in relation to the temperature of the free stream. In CFD, you're modeling that directly. You can calculate that based on the actual results of your analysis, because you're modeling the flow. You're simulating the flow directly as it's picking up that energy and running away with it. Natural convection is a bit more difficult. What it is natural convection will happen when you have a hot surface or a cold surface, and that will actually change the density of the fluid. Okay, and the density of the fluid changing will create a buoyancy effect, and that fluid will either go up or down based on whether it's higher or lower density, lower or higher. So it'll go up if it's lower density and down if it's higher. And that'll actually kind of convect energy away. So what we do is we need to activate gravity. So you can see here that when we're looking at our natural convection formulation, we're looking at gravity. Okay, so we need to have that because that's what creates the buoyancy effect. When we have our lower density, it's the gravity and the potential energy of the gravity, that difference in pressure, that pushes the lighter air up. Some helpful coefficients for calculating and understanding whether or not you're a natural or forced convection dominant flow, because if you are forced convection dominant, you don't need to have your gravity turned on, because not much of the flow is going to be being convected by the difference in density. Most of it's going through forced convection, which is a velocity. The flow is being forced through inertial forces. This is where we turn our gravity on. Here we give it a direction, and then we can specify our operating temperature and our operating density. Going to skip through here. We're going to look at radiation. So radiation is another really important one. It's not valid for all scenarios, generally valid for higher temperature scenarios. So radiation is where we're getting that electromagnetic kind of heat transfer, thermal radiation that happens when you've got really hot surfaces. And that goes from wall to wall. And you can see here that it's based on some Stefan-Boltzmann constant, which, as it says, is a constant. The emissivity of the materials. So if black body is the most emissive, white body is the least emissive. And you can see here it's a function of the temperature difference to the fourth power. Okay, so really we only really consider temperature radiation as a heat transfer mechanism when we've got really high temperatures, because generally it's actually quite a insignificant or negligible energy transfer phenomenon. So there's a couple of different models which I won't go through. Getting a bit more advanced here with our CFD modeling, discrete ordinates, surface to surface, Monte Carlo, all of that stuff's in the help there if you wanted to do any radiation modeling down the line. So quickly go over some solver conditions before we go back to our model and try to ascertain what's going on there. Solver conditions, just this is all reiterating, which I think is really important because there's a lot to get through with CFD. But in our setting up physics in our solver, generally our major type is either pressure-based or density-based. And remember, we use density-based for Mach numbers above 3, pressure-based for everything else, generally speaking. And then we've got, and you can see here that the difference between our pressure and our density based. When we do density based, we're actually solving all of this stuff at the same time. It's all coupled in. Okay, because when you think about it, you've got your ideal gas law, which is pressure times velocity is equal to mass times the gas constant times temperature. So all of these things, so temperature and all that energy and density is all in here already. So we go straight from energy and species, which is usually density-based solution, straight to solving the turbulence equations. Turbulence models, we've been through that. So I'm just looking at these slides to see what's really important to get through. This is looking at the difference between a simple solver, which is our segregated solver. Remember, we're solving our mass, momentum, in the U, V, and W directions, or our X, Y, and Z directions separately. In our coupled solver, we're solving them all together. Now, remember, that's going to use more RAM because there's more kind of variables in the equation that we're solving for each element. But it should converge quicker because we're doing them all at once. So more RAM, less iterations. And also, generally, a more stable solution, generally speaking. There's a lot of these things that we like to say generally with CFD, and any of you who use CFD long enough will find the exception to the rule in every single case. It's a very complex phenomena, CFD itself. So just know that when I say things that are general, aren't always hard and fast rules. These discretization methods, okay? So we generally have like first order, second order. We'll forget about these least square cells gradients for now. We'll just think about first order and second order. So when we're looking at flow variables, things like density, pressure, velocity, they're a function of the gradients around them, okay? So the gradient is generally what forces the difference in some variable. Now, to get an accurate understanding of what the gradient is, we use discretization schemes, okay? So we've got some value in this cell, some value in this cell, and some value in this cell. The gradient for a first order scheme is looking at this cell and this cell, okay? So the difference between the two, so you've got some value here and some value here, and that's the gradient. Using second order takes one more step, okay? So now you've got this value here, and then this value here, and then you're getting an averaged gradient. So it's more accurate, right? So when you're doing a second order, you're taking a more, a larger equation essentially with more variables, so you're using more RAM, but you should be getting more accuracy because you're getting a more accurate understanding of what the gradient is between these couple of cells, which is going to give you a better understanding of what the flow variables are for the next iteration. Okay. Now remember what I said about direct numerical simulation. So direct numerical simulation, if I can take us back there very quickly, is our turbulence modeling when we're looking at directly modeling all the turbulence. One of the things we have to do a proper direct numerical simulation is have higher order spatial discretizations. So upwards of third and fourth order spatial discretizations, because that gives us higher accuracy and allows us to pick up more with less elements. Okay. So in Fluent, generally it's more of a commercial solver. You're basically using first or second order. Generally, you leave it all second order. I think first order is okay for turbulent quantities. So we don't have the higher order spatial discretization schemes, but as we went through before, the direct numerical simulation is helpful for not really anything outside of really high level academic studies. So we're looking at same mesh, same boundary conditions, first order, second order. There's a difference there. Same here. Look at the second order versus the first order. So it's really important to understand second order will generally be more accurate. So under relaxation factors, I went through before. So you've got some pressure value in a cell on iteration 1. On iteration 2, you've got a different pressure value based on the difference between the iterated calculation. And whether you apply that full difference to that pressure value or only half of it is controlled by these solution controls, these under relaxation factors. So we're only applying half of the difference, okay, in this case. And you look here, you can see that means we're stepping more gradually towards the solution when we're only taking a fraction of that next value. And so what it means is you can see here, we've got a very stable solution. It's very consistently heading down, but it took 225 iterations to reach the same result. So when we had our under relaxation factors at 0.1, we got a very stable solution, just took a long time to get there. Here, we've got less stable, kind of went back up and down, but then turned stable here, sorry. You can see that we've reached the same value, converged quantity of interest with a higher under relaxation value. So reports are really important. So let's go back to the model and let's talk about convergence. Okay, I mentioned it before that we've got our residuals and we've got our monitors, the two main ways that we're going to assess convergence. So we've lost our lift plot because I was playing around putting extra contours on. But we have solved now. You can see we've solved for 200 iterations. It's gone all the way. It hasn't converged. So because we haven't reached the 1e to the -3, which was the criteria, if we go back and remember that, we look at these residuals, our convergence criteria is 1e to the -3 for all. Okay. So we haven't actually converged in terms of when we're using our residuals to ascertain convergence. Remember, residuals are the difference between the left-hand and the right-hand side of the equation of our Navier-Stokes equations. And so what we did is we put in a monitor. So a monitor is our quantity of interest. So we're assessing what the value of drag and downforce is at each iteration. And what we would like to see is that become flat as well. So we haven't got that either. Okay, so we haven't really converged to a solution. And the reason for that would probably be, for this case, if we look at our residuals, they haven't really dropped that far, but what they have done is they've gone into this oscillatory pattern, okay? That's a really good indication that we've got transient flow phenomena. So if we wanted, so there's a few things that we could do to try and get this, the residuals better. And if we couldn't get them to converge fully and we couldn't get this to flatten out fully, then we might have to run it transient. Okay, so the two methods of assessing convergence: our residuals, difference between the left hand and the right hand side of the equations, and our monitor points. Okay, so you can see here that we have converged to a point, right? We have converged somewhat. So if we take it from about the 100th iteration, we're looking at a difference of about 28 and 30 newtons. So about 2 newtons, within about 2 newtons, we're kind of converged, okay? Now, based on engineering judgment, that might be converged enough for you. But I would say that if it was your first run, there's a lot we can do to try and get a better convergence behavior. Okay, the first one might be to reduce the timescale factor. That's like our pseudo transient under relaxation. So when we go back into here, we're using coupled pseudo transient. Our timescale factor is our pseudo transient timescale factor. So we could reduce that to 0.1 or 0.01. And we would run that further and see if we could get this line to flatten out and we could get these to drop further. My guess is we could get them to drop further, but not to converge fully. The other one that we could do, we just went through our controls, our under relaxation factors. So we could drop all of these values right down to 0.1 or to 0.2, 0.3, whatever, to see hopefully this drop because we're using a more incremental step towards our solution. Okay, so we're being a bit more gentle with our solution progression. So those are the things that I would do. Now, some of the things that we could do with that as well as we could go in and do contours of our highest residuals. So we can turn on expert parameters. Let me find that in the slides. Hopefully I can grab it. Okay, so it's right down the bottom. So in the slides, you're going to get a section on troubleshooting. If you run this 2e command, remember I went through 2e commands, you could basically copy that into the text user interface. Solve, set, expert, yes, yes, yes. That's going to give us more options for looking at the residuals as a contour on the flow field. Okay. So if we had specifically high residuals on one of these parameters, we could then plot that contour. So let's do an example of that on this. We're not going to do the expert parameters. Without the expert parameters, you get just the continuity. So we look at this, we got continuity, X, Y, Z, K, and omega. So let's do an isosurface. So an isosurface is a specific type of post-processing tool that allows you to put a surface where the variable, where one variable is equal to that exact value. So you might do it for velocity. So one way you might use isosurfaces is if your velocity is in negative Z, which it is, you might do it for Z velocity and put the ISO values where the value is 0. So it ranges between negative 36 and 16. So it's coming in a negative. We've got this, you can see here the flow is coming in at negative Z. But we've also got, in some regions, 16, 17 meters per second in the opposite direction. And that is basically due to, that would be on the wheel, I would say, but there will be other regions where it has separated as well. That tells us where the flow is going in the opposite direction. It tells us where it's separated. Okay, what we're going to use the isosurface for is to look at regions of high residuals. So you can see our mass balance residual. We're going to look at some value. Okay, you can kind of narrow it down further and further, but I think up here is a really good. So everything within this surface has a higher residual than -3 to the -6. Okay, and so we can see that our problem areas are actually mostly not around here, but around here. And the reason for that might be because we are in the wake region. A wake region is generally highly chaotic flow. Like if you've ever been behind a truck and you wound your window down, you know that the wake region is highly chaotic. You'll have wind blowing in 1 second and then not, and flapping all over the place. So because that's highly transient, maybe that's why we have higher mass imbalance residuals here, because we're trying to get a steady state solution for something that's not steady. Okay, so that's using these tools to try and get an understanding of why maybe we're not converging. Okay, so that's one post-processing method. So one thing we might do here is we might be able to ignore it. We might just change our under relaxation factors. There's a few things we would do. We would just have to run some tests and continue to solve until we were happy enough with the result. Okay, what else can we do about errors here? So let's just assume now then, let's assume that we have a converged solution. And we're going to do some post-processing. Okay, so the first thing we're obviously going to be looking at is, like if we consider our solution to be converged and accurate, we'll be looking at these values here. So you can get these out either here because we've printed to console through the solution, or we can do a results forces. We're going to look at negative Z on everything but the ground, and we're going to print that out. You can see we've got a total negative Z. We're looking at drag. We've got a total drag from the chassis of 8 newtons, front wing of 6, suspension of 2, and wheel of 10, and a total drag of 28 newtons. Okay, so obviously our wheel, like I said before, if anyone who's worked on FSA vehicles, the wheels are the most troublesome part when it comes to CFD, because you really going to cause you the most drag and generally going to cause some lift. Let's see if that's the case. So we're looking for downforce. 57 total, all of it being produced by the front wing. Chassis producing a little bit of lift. Suspension's producing a little bit of lift, and the wheel's producing a lot of lift. So let's do a pressure contour to see why it's producing lift. So we're going to do a contour, we'll call it pressure. Okay, so we can see we've got, oh, we're in turbulence still. I thought it didn't look very correct. Here we go. Okay, so now it's a little bit hard to kind of pick up what's going on here because I don't like the scale for looking at aerodynamic simulation. So I'm going to show you a really cool way of doing a better scale. So we're actually going to change it to split between two colors. And that way what we can do is we can have a better understanding of what's pushing and what's pulling, what's high pressure and what's low pressure. So we're going to apply that. We're going to edit. Okay, let's just apply that, see if it comes up. There we go. Okay, so but what we want to do is we want to have this white one, this white section, this middle point at the 0 pressure region. Okay, so you can see here that we've got a minimum pressure of 1500 pascals and a maximum pressure of 182, sorry. So we're going to run a quick calculation. I'm going to use Excel over here. So we're going to go 1575 is the minimum, and then 183 is the maximum, and the difference between those is about 1758. And we'll get the ratio of the maximum to the total to get the midpoint. The midpoint's at about 10% from the far end, so we can call this 90. Right, and then we're going to move these. We want to keep that one out because I don't like that one, but we're going to put this one as far. Try and cover that one if we can. Yep. In between there, and that one in between there. Right, so everything above that point is going to be green, and everything below this point is going to be blue. So let's apply that and see how it looks. There we go. So now we have a better understanding, a much easy visual tool for picking up where is pushing and where is pulling. So this is pushing on the top surface of the front wing, so it's pushing it down. On the bottom, we've got a blue, nice blue color. It's sucking down because we've got a low pressure region under the front wing. We've obviously got a high pressure region here, dark green for the stagnation, right? So the flow's hitting that. Same here. And you can see here we've got big blue surface on the top of the front wheel, right? That's causing a lot of lift. We've got a big green surface on the front end of this wheel. That's causing a lot of drag. All of this blue is pulling the chassis upwards, causing lift. This blue here is sucking it down. That's good. But this one here is pushing it up, and all of that there is pushing it up. So automatically, just from that contour alone, we can go, okay, let's change the shape of the front nose. Let's flatten the bottom out. Let's not allow as much air to get into here. And maybe let's keep this kind of bubble region to see if we can keep some suction under here. Maybe get some venturi under here. Also, we might try and spoil the flow along here, or change the shape so it's not so bulbous, it's not so airfoil shaped, because that airfoil shape, as the flow stays attached and increases in velocity, is what's reducing the pressure and causing that suction up. Okay, so there's some really quick ways of assessing the design of our wheel just from some handy tips on creating a better visualization tool. Alrighty, some other things that we might do. We've already seen vectors, so I won't make another vector plot, but what we can do is we can create some planes. I'm going to do a few. Where's our plane pool tool? There it is. So we might create one here, 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 and we can use that for a bunch of different things. So obviously vectors is one. Let's create one anyway on there for sure. Okay, let's use this one. And then let's add this to graphics. So we can look at it both at the same time. We can use some options in here and changing the scale of these vectors. You can make them fixed length, so they're not a size is proportional to the to the magnitude of velocity. So you can see here we're coloring by velocity. And that's going to be a really helpful tool to understand where the flow is separating. So you can see we've got a big separation bubble in here. So we might want to turn this off. So what we can do as well is let's put them together so we can see them together, but we'll make one a little bit transparent. Pressure contour, we're going to add in our vector contour, and we're going to make our pressure contour 90% transparent. So we've got a good context for what's going on, but we can still see the vectors. Alrighty, so it's actually staying attached at the wing, but we do have a recirculation region here in front of the wheel, which is, makes sense. It's really hard to deal with these wheels. There are some really helpful things that if you look at aerodynamics, Formula One cars, you can see that they've got some really crazy end plates that try to capture vortices and throw the flow out away from the wheel. So you don't have as large of a high pressure region in here, but looking at vectors is a really good way to ascertain, okay, where are we separating? We're separating exactly here on that front wheel. And that separation bubble is quite large by the look of it. So if we were to go and put a velocity contour on that same surface, might be a better way to see what's going on. Yeah, you can see the separation bubble's quite large. So not only do we have the high pressure here from the wheel that we looked at before and the low pressure on top, but we also have this massive recirculation region. If you think about what's happening when you have a recirculation region, is the energy that you're putting into moving forwards is being taken out by the energy of this flow, because the force you're putting into moving forwards is actually creating chaotic flow behind you. So the energy that you're putting into moving that flow is being taken away from the energy that you're trying to use to go forwards. So this large separation bubble is a problem, and you can see that really well through this velocity contour. Alrighty, we'll quickly make a streamlines, and then we'll go to questions. So let's have a look at, so we want to create a streamline. We can do that from a surface or an edge. I'm going to create a small surface just quickly. So we might use a ISO surface tool like we did before, but what we're going to do is we're going to use the value of Z coordinate. Compute, we want to be about 1, I think. Let's see where that is. That looks good. Okay, and we're going to clip that. ISO clip. We're going to clip this ISO surface to about more values of Y. Compute, we want a max value of about 0.4. Create, and then we're going to clip it in X as well. So a little bit of a process to get one of these going, but it's worth it in the end. So 0.6, say. That should be about right. Let's display and then add to graphics the pressure contour. Okay, so that's a decent surface from which to generate streamlines. You might want to make it smaller. Say you really wanted to understand what was going on with the flow around this end plate. You might make a really small one just here, so you know that the flow that you're analyzing, the streamlines are coming straight off the end plate. You can see what they're doing, but we're going to do a very general one here. So now that we have our surface, we can create a path lines that is generated from the last clip that we did and colored by velocity. Alrighty, so let's add that back to graphics. So you can see we've got a vortice rolling off this front wing, off that end plate, because the high pressure is pushing the flow out, and it's rolling off around that front wing, and it's actually joining into the wake. So what they do with F1 cars is they create a vortice on the outside, and they create a vortice on the inside as well. And you have quite high energy flow that pushes the vortice, and then they use barge boards to push those vortices out. And what that does is it takes this kind of wake region and moves it away from the vehicle. This low energy flow goes away from the vehicle and opens it up for more high energy flow to come in and hit the lifting surfaces. Okay, so streamlines are a really good way to ascertain where that flow is going and what it's doing. One thing we didn't do, which we should do whenever we do a symmetry plan, is put the full car in there, because it looks better and it might help you to better visualize what's going on. Okay, so I have got a couple of different models I can take you through the setup of if you want to see it. We can open the floor to questions about people's projects, general questions, if anybody has anything specific to something they're working on. Or, like I said, I can take you through a overset case, the setup of an overset case, and the setup of an adjoint solver case. Up to you guys how you want to progress. Or we can call it. It is past 11 now. Does anyone want to throw a vote in there? If not, I'll just move forward with, I'll show you, go through the setup of a couple of different advanced models, and then we'll call it. Okay, so let's go back to these slides then for a minute. So in the section of the slides you get, we'll go look at these advanced options. In here, we've got a joint solver, mesh adaptation, surface wrapping, journaling, which we spoke about, and overset meshing. So I'm going to talk you through ADJOINT for those who are interested. It's really interesting. It's really cool. So what the ADJOINT solver does is it takes your flow solution and calculates the adjoint equation. The adjoint equation is a mathematical technique that helps you to find an optimized solution for specific variables that we call observables. And so what you can do is you can solve the adjoint equation. It'll tell you where to move the mesh, and then you'll move the mesh, you'll resolve the equation, you'll resolve the flow field, you'll resolve the adjoint equation, you'll move the mesh again, and it's an iterative process that should hopefully let you end up with a optimized aerodynamic shape. Okay, so in this case, I think that was optimizing for lift over drag. There is a tutorial that you can do yourself. You set your observable, what you want to optimize for, lift over drag, and it's going to create more lift for less drag, step by step. So we did a representative propeller for a support case, just to get them started on using the adjoint solver, and the purpose behind it was to get a better thrust over torque. So it's like lift over drag for propellers, and a better thrust over torque would mean a better noise performance, because obviously we know with quad rotors, some of the biggest issues that we're having with them are they are too noisy, and the noise is unbearable. It's quite high pitched and annoying. Okay, so for this case, I did show it to you briefly before. We have obviously our large domain, and it does have quite a funny shape. The reason it has a funny shape is because we have an inlet on the top and our outlet on the bottom, and it goes all the way down the bottom. Now, the reason we do that is because we don't really want to have any walls when we do a rotating reference frame. So remember, this whole thing's rotating, but when these are outlets, they don't have any effect on the flow. It's theoretically rotating, but when we have a wall there, it's going to take some flow with it because of boundary layer effects, right? So what we have to do is we have to have it all outlets or inlets. And the shape of this is because we want to be able to resolve the flow field for the length of, where we expected to see kind of disturbed flow. But we want to have as few reverse flow sections as possible. So what will happen generally is you'll have flow coming down, being forced down by the spinning propeller, and it gets a little bit more chaotic out here, and you'll have some going out and some coming in, right? And that can cause a problem for convergence. In most cases, it's not really a problem, but for the case of adjoint, you really need to have a well-converged, low residual solution, and the lower the residuals, the more stable your adjoint solver convergence is going to be, and that can be tricky. So we made the domain shaped like this to reduce reversed flow and make sure that we were getting a converged solution. Okay, so we've got our inlet, our outlet. We've got a periodic boundary here. So if we just add that to graphics, this is periodic, so it's split down the middle. So essentially, we're saying this thing is symmetry, is rotational periodicity, which means that this surface on the left is going to transfer its data to the surface on the right as if it's spinning around, right? So as if it's the same thing on the other side, but rotated 180 degrees. Okay, so that's obviously there to cut down on mesh elements. So if we were to solve this for the whole propeller, we're going to have double the amount of mesh elements. But if we do rotational periodicity, we can reduce that by 50%. You can see here, we've only got 700,000 cells. Now, this is not a super accurate model. It's more of a test case to say, hey, look, this is how you set up an adjoint solution. So 700,000 is quite a low cell count, but it means we could solve it on our computer here. Now, we've got all these walls. These are the walls of the propeller. Okay, so I've just separated them out so we could have better controls for our adjoint solver as to where we move them, or how we move them. So we're doing a steady solve, pressure-based, K omega SST. Let's do a quick plane to see how well we resolve the boundary layer. Here we go, surfaces at the tip. Edges, all edges, save display. 1, 2, 3, 4, 5, 6, 7, 8 layers. That's better than the last time, but still, like I said, it's a representative model. We could probably check our Y plus value to see how accurate we're being with our model. We're going to plot that on all of these walls. We want to take off global range so we can have an understanding of what the actual maximum range is on here. So we're doing between a Y plus of 0.02, which is very small, and 14. So it's actually done a fairly good job of picking up the boundary layer for a representative case. Obviously, we want more layers because we want to pick up, the more layers, the more accurate we're picking up the gradients in the boundary layer. And 15, upwards of 15 layers is going to be what you're targeting when you want an accurate simulation, but we've done a better job. Okay. So what else? Our material is, we're not going above a Mach of 0.3, so we can have a constant density and a constant viscosity. We don't have any temperature effects, so our energy is turned off. We're using coupled solution, pseudo-transient, with our default under relaxation factors. We've got a couple of reports created, one for thrust and one for torque. Those are our outputs of interest. And then what we would do is we would solve this for our standard, for our general flow field. Okay, so we've got our solution. We've dropped below e to the -3, so we've done quite well, but we can see we've got some transient behavior still being picked up, but that's okay because we've dropped below our certain criteria. So we want to have good convergence behavior, remember, because that's going to give us good adjoint convergence behavior, because adjoint uses the flow field solution, but it's a whole nother solution altogether. Okay, so once we've looked at this and we've said, all right, so I've got a good solution, we know what our values are for torque and thrust. We go into our design tab, and then we create an observable, and our observable is our object of interest. So we've got our force, which is our lift value, our moment. So we've created all these, and we've also created a ratio, which is another object that we've created. Let's manage that, sorry. So you can see we created a create ratio, and then you get numerator force, denominator torque. Okay, and we've just evaluated that, which means, and we can see that our current value of torque, of lift over torque, thrust over torque is 41. So we're trying to maximize that. So we can see it created our observable. We want to maximize that. I won't go through this stuff too much because it does get very high level. There are some intricacies in the ADJOINT solver as to how to get stability, but you want to match these up as much as possible. Solver controls, there's some solution-based initialization, there's some auto-adjust controls, and there's some stabilization settings. These become really important in order to get a joint convergence. Residual minimization scheme is a really helpful tool, that numerical tool that it does uses to get convergence. Monitors, this is just our ADJOINT residuals. So one of the things about the ADJOINT solver is it doesn't currently, I think in the newest release it does actually, but it's still beta, so it's not recommended to use. But what it does is it keeps K and omega, so the turbulent flow field, constant in the ADJOINT solution rather than solving and optimizing while updating K and omega. So it's a limitation that's a frozen turbulence field. So you can see we've only got residuals for the ADJOINT continuity, the ADJOINT velocity, and the ADJOINT flow rate, not the ADJOINT turbulence quantities. So then what we'll do is we'd calculate, initialize and calculate our ADJOINT solution. So it's calculating that based on the observable and these stabilization parameters that we're after. And then hopefully we would get some convergence, and we go into the design tool. And we use this to look at how we're going to move the mesh and in what region we're going to move the mesh. So let's quickly display. You can see we've got a box added for our design tool, and that is because we've got a region here within which we're going to move the mesh. So in this region, the mesh is able to move. So that's going to constrain it. So this mesh can't create an infinitely long, the solution can't create an infinitely long airfoil. And those in this region, you can see there are control points, and in each one of these control points, there's a certain amount in each direction. So each one of these creates a little box, and it's within that box that we're going to move the mesh. So the more control points, the more control, or the more finer the mesh movement you can have. So the objective is to maximize or have some target change in value. You might increase it by 1%, you might increase it by 10%. And then you'll say which surfaces I want to be modified, and then you'll calculate design change, modify, and then that's move the mesh. Now, numerically what it is when you're solving the ADJOINT solution is you're solving for derivatives. Okay, you're solving for the derivatives of those solutions, those observables at each point on the surface. And what that means is you're getting a linear approximation at that point. CFD is highly nonlinear, so when you actually move the mesh, if you move it too far, you may not get the expected behavior change because you're calculating a linear derivative at that point. So when it comes to making ADJOINT solutions, you want to be doing a lot of iteration. So you move the mesh a very small amount because that makes your linear approximation more valid. And then you go back and solve the flow solution with the new mesh. And then you go back, calculate the ADJOINT, run the mesh morphing, go back and solve again. Okay. So with this one, I'll show you some of the results that we got out of it. Alrighty. Sorry, trying to find these images. So at the start, we're looking at a pressure contour in the middle of the wing. Okay, so that's at the start. So what we're looking at is we're looking at a pressure contour around here. We're looking at the pressure around the airfoil. And then let's look at it for the optimized mid-wing. I'll put it on the side. There we go. So you can see that it's a subtle change, fairly subtle change, but you can see that there's differences in the trailing edge. You can see here, I've kept it the same key as well. So the same maximum and minimum pressures. You can see that there's a much larger low pressure region. It goes further back. So in this case, we're looking at L over D. This one I've actually maximized for just thrust as well. So let's look at that one. You can see here a bit more of a drastic change between the start point and this one in terms of a much darker blue. Okay, and then this tilted down trailing edge keeps the flow attached, I assume, for longer. But that's the thing with the adjoint solver. It's really cool, as in you can try and it doesn't do it based on a kind of an external overview or understanding of aerodynamics. It does it based on these small derivative understandings where you're kind of moving it little bit by little bit and getting better and better results every single time. Let's see if there's another cool image I can bring up. So this is an oil flow, which is one of the post-processing techniques you can use with path lines. You can do oil flow from this surface. Look at the thrust max oil flow. So the one that was optimized for maximum thrust. Now you can see that it's hard to see the shape change exactly, but you can see that we've twisted out this trailing edge to keep the flow attached for longer, and that's going to allow more of that force to be realized. So it's actually increased the size of this end point, and you can see that the flow is actually in less separation. So you can see there's little separation bubbles here. In this case, this is the start point. There's a lot more of these separation bubbles and a lot more of the flows being thrown over the edge because in this case, there's nothing stopping it. In this case, this face is actually lifted up a little bit, and this trailing edge is extended out, which keeps the flow attached for longer. So it's actually producing far more force than it was originally. Let me see if I can just get the actual values of how much we increase the force. Okay, so we increased the thrust by over 30% in the case. So that was our start point, normalized. And then our final point was 30% increase in thrust, just based on the adjoint solution, moving it increment by increment based on the derivatives that were calculated. If you're interested in that, there is the tutorials on the learn.lepost website, which is you'll be able to find in here. Okay, so on the learn.lepost, the site that I showed you before. Okay, the other one we're going to look at very quickly before we call it a day is overset meshing. Okay, overset meshing is a high-level CFD method that allows you to have multiple different cell zones and communicate the flow variables between the cell zones. And the reason you would do that is because you want to be able to have these regions moving in space. So you can see that we've got this background mesh, component mesh, and these components you want to be able to move in space. There we go. And that's really difficult. You can do it without overset, but you have to constantly remesh, and that's called dynamic meshing. I'll show you where they are on here. So this is the case we're going to be looking at. In here, you can see we've got dynamic mesh turned on, but we're not actually remeshing. When we don't have overset on, you need to remesh. So there's smoothing, layering, and remeshing methods that you can put on. Each of those has their own intricacies and things that you have to understand. But with overset, you don't have to remesh, which means you're not compromising your mesh quality, potentially. That's the difficulty when it comes to remeshing, is you can get into situations where your mesh quality is compromised and then your solution blows up. Because remember, we need to have a minimum orthogonal quality that is above 0.1. We also need to have a high enough mesh count in all of the areas to pick up the flow phenomenon. Okay, so when we're remeshing with those, some of those things might be compromised, but with overset, you have what's called a background mesh and a component mesh, and then an interface between the two. So you can see here, this is the case. So it's a 9 million element case. We've got our background mesh and then our component mesh, and that component mesh has the store in it. So what this case is, this is a store drop-in case where we want to watch, we've got the flow coming in at Mach 0.95, and we want to know what happens to this store, this bomb, as it falls away from the wing. We want to ensure that the stability, the lift stability of the wing is correct. And this is basically just a representative case. Okay, so this is a validation case that was created some years ago that you can use to validate your code against, to make sure that you're getting the same results as the validation case, the original validation case. And let me just reiterate, I'll show you this mesh again. So you can see that we've got our background mesh and then our in our component mesh. And if I show this contour is showing the different cell types, and the different cell types like mesh cell types. So 1 and 2. 1 is solve cells, 2 is donor receptor cells. So that is these are all standard solve cells. When we get to these cells, it's actually communicating information between the component mesh and the background mesh. And there's a little overlap, and then between the background mesh and the component mesh, and then that flow's coming and hitting the store and then going away. So it needs to communicate in and then communicate out. Okay, so it's basically then what that means is you can have this whole background mesh, this component mesh, sorry, moving in space without remeshing, because it just changes where the interface is, where you're communicating between the two. Now, there's a couple of things about overset. It's not conservative, so it's not mass conservative. So that does make it a little bit tricky when it comes to accuracy. You need to check your accuracy. You need to be able to validate against some solution, some other experimental data, or some validation case, which is the case in this case. But it is a really helpful tool because you don't have to remesh. Okay, so let's just look at the results from this one. I'll take you through the actual full setup. So we've got our mesh was 9 million cells. I showed you that before. We've got our dynamic mesh turned on. So in this case, tick dynamic mesh, tick sixth-off, and sixth-off is another solver. Sixth-off says, okay, which region is moving in space using a sixth-off solver, and what are its properties? What are its mass properties? So in this case, we use a UDF. That will tell it. Let me see if I can quickly bring that up. So the UDF we mentioned very briefly before. Yes. Okay, here it is. So UDF comes from in here. So you put a UDF into here, user-defined functions, and that's a snippet of code that comes in that adds information to the solution or can add functionality to the solution. So in here we've got our mass properties of the store. So we're actually going to apply these to the store. And then they have our rotational inertias as well. So that tells it based on the pressures coming in from the flow field, how much it's going to rotate in time, how much it's going to translate in time. And there's also an additional here, ejector forces. So there's something pushing the store away for a short amount of time. Okay, so you can see here we've got a sixth-off solver turned on. And then we've got our dynamic mesh zones. So our store, first one, it's actually the properties of the UDF haven't been loaded onto this session, but the sixth-off properties here you would be able to put in your UDF properties for that you loaded in up here. So the mass and the rotational inertias. You put your center of gravity in here and then sixth-off on. The overset is the rest of the cell zone. You need to turn that on and make it passive. So the forces on that cell zone are not pushing it or pulling it, but it's moving in the same way as the store is. Okay, so it's the forces on the store that are moving both the component grid and the store walls, which is this bomb walls, at the same time. Okay, so we're using K omega SST, and you can see that we're also got energy turned on. And the reason for that is we have compressible flow because we're doing transonic flow regime. We're actually having a Mach number of 0.95. So energy is turned on, and then in materials, you can see that we've got our ideal gas law, which means that our pressure is a function of our density, the gas constant, universal gas constant, and the temperature of the flow. Okay, that adds in a few more things that you can put in and tune for your temperature. Like I said before, you can have viscosity as a function of using Sutherland law, things like that. All righty, let's quickly go through the boundary conditions. So we got 2 cell zones, and we've got an interface between the two. Quickly go back and show you that. We've got overset interface here. So overset interface between the background zone and the component zone. Those are those 2 different cell zones, so enclosure and overset. And those are our 2 cell zones here. And then we look at our boundaries. Our far field is actually all of the flow around it. So this is a different type of boundary condition that you haven't seen yet, but this is used for transonic and hypersonic flows. Okay, so this plane here would be a symmetry, but this far field encapsulates the whole thing. And you can see that you specify a Mach number and a gauge pressure. So we get a Mach number 0.95. So it's almost speed of sound. So we don't need an outlet because the flow is just going through the far field all in the same given direction. You can see we specified the component direction. So overset is our overset interface that we created before. And that's basically the outside of that component mesh. And then we've got our symmetries and then our walls. So I'll show you what the result for that looks like. As the store falls away, on the left, we've got a pressure contour. And we've taken an animation. So when we do a transient analysis, you can take an animation that takes a snapshot every 1 iteration or every 10 iterations, and then it plays it back for you in animation. On the right, we've got density gradients. So you can turn on expert parameters and plot density gradients, and that allows you to see what is effectively the Schlieren, which is what you see when you do hypersonic wind tunnel analyses. So that kind of data, we'd be looking at the translation in X, Y, Z, and the rotation in X, Y, Z, and also maybe some pressure cuts across the bomb to validate against another case to ensure that we're doing the right thing. Okay, does anybody have any questions regarding those cases? No worries. Everybody go on to learn.lepos.com.au. I will be available to contact for until 12. Was it message? No worries, Roberto. Now I will be available to contact until 12. Jump onto the learn.lepos.com.au, make an account. I cannot stress that enough, that how valuable this stuff is. Have a look at some of the space claim, fluent meshing, turbulence, anything you're interested in, tutorials. There are also some suggested tutorials, sorry, mixing my words, on the slides when you get them. Also the ADJOINT solver there. Have a go through some of the tutorials. I think it'd be really important for you to do that after listening to somebody blabber on for 2 days, for Hashan and myself. To give you a better understanding of what it is that we're talking about. So getting started fluids might be a really good place to start actually there. So you can see you can do that. The space claim skills, then you'll be looking at flow in a pipe with some temperatures in there. Yeah, have a run through some of those, and yeah, I'll be here to answer any questions if you need.